In teleoperation, it is often required for a robotic manipulator to perform a fine motion in a large workspace. A micro-manipulator attached to a macro robot system has been proposed to meet such needs. To demonstrate vibration and contact control, we created a test bed of an industrial hydraulic manipulator as a micro-manipulator and a 12-foot-long link as a macro-manipulator. The motion of the micro-manipulator with a conventional PD controller can easily excite the macro-manipulator. These structural vibrations can last more than a minute and have detrimental effects on safety and efficiency. However, with inertial force active damping control, the micro-manipulator counteracts the structural vibration using strain gauge feedback at the base while it follows desired positions. Both horizontal and vertical vibration damp out in less than 2 seconds. If an external impulse is applied at the tip, the vibration in the vertical and horizontal directions can also last more than 1 minute. Again, by applying inertial force active damping control, the controller can damp out the vibrations in less than 2 seconds. The micro-manipulator is teleoperated by a spaceball input. When an arbitrary path is applied by the operator, the manipulator oscillates and cannot follow the exact path. With inertial force active damping again activated, the manipulator follows the exact path without the vibrations. In another example, a digital force-torque sensor was attached at the wrist of the micro-manipulator, and a force controller was implemented to the manipulator. As a force is applied to the sensor, the hydraulic manipulator moves accordingly. When a force-controlled manipulator makes a contact with a very rigid surface, it is well known that the contact instability occurs. The frequency of the limit cycle depends on the link compliance and force controller gains. Again, with inertial force active damping control, the manipulator can make a smooth transition to a contact without chattering by dissipating impact energy. To demonstrate that the contact force is being regulated, a paper cup was used. Using the force-torque sensor at the wrist, a small force in the horizontal direction is controlled. And as we can see, the cup is not dropping or being crushed. Holding a cup against a wall is a relatively simple task since the cup is very flexible. This time we experimented with something not so compliant, a fragile egg. Again, the manipulator is force-controlled in the horizontal direction. The manipulator contacts the egg and regulates the holding force to be about 1.5 pounds. Any overshoot or chatter of the force control will break the egg. Here, a hydraulic manipulator system with an 18-foot-long reach running at 3,000 psi is holding an egg against the wall. To further demonstrate the system, an operator performs a teleoperation task of inserting a peg in a hole with visual information provided by a video camera. With the proposed controller, an operator could insert a peg in a very tight hole with a clearance of 10/1000ths of an inch. The force control makes fine alignment adjustments that visual information cannot provide. The inertial force active damping controller eliminates the vibration before and after the contact. Using an industrial manipulator testbed, the vibration and contact control of a flexible manipulator is demonstrated. With the proposed control, the micro-macro manipulator will be able to perform a fine motion in a large workspace accurately, efficiently, and safely.